What's going on, everyone? It's time for another session. Let me get things going up. I'm trying this new thing with Windows virtual desktops. It apparently does have the capability to do this, but I'm still trying to figure out how to get it to capture just that desktop rather than the full screen in OBS. So haven't quite figured that out yet, but we're working on it and kind of make things a little bit better. It is frustrating not having a second display and having to kind of like do multiple computers here. But let's see here. All right. Just making sure everything's working. Looks like we have audio coming through. The stream is running. Everything's good to go. So where we are from last time, we have decoding working of all of the jump instructions. So we can parse and decode all the jump instructions. We can parse and decode all of the single operand instructions, but we don't bring them into an intermediate representation that we have right now. We're only doing it for ret I and call. Actually, let me pull these up really quick. We want this, and I think this. Yeah. So tonight, what we're gonna finish doing is getting the rest of the, making sure that our decoding is correct for these single operand instructions, and then getting our instruction representation in memory correct. Something that I realized, and I think I mentioned it last time, is that both the representation we have right now in memory and some of this parsing are both very, very bad. We're probably going to stick with the current representation of the data in memory for now. But I think probably in the next stream or the one after, we'll probably end up rewriting it. Something's a little bit better. Kind of my idea right now is that we'll get single operand instructions finished, tested, and working. And then either we'll redo the internal representation or we'll build the two operand arithmetic stuff first. And I know that we're going to have to redesign our internal representation before we get to printing, because printing this is going to suck, and I have some ideas about how to do it better. But we're going to have to do that before we get to that point. And I don't know if it's going to be easier to overhaul all of the internal representation before we move on to the next set here or after. But not important for tonight. Tonight we just need to get the rest of this working, get the testing working. The other big thing that we're going to refactor is we're going to end up moving a bunch of this code out into multiple files. Right now this is a huge mess. We're at like 400 lines of code, and it's difficult to work with. So we currently we have one call variant that we've implemented, which is our calling an individual register. We're going to want to write tests for a few more of them. So call should always be 16-bit wide value. Is it 16? Yeah, 16-bit wide value. We can verify that this works correctly or doesn't. I'm not exactly sure right now if it's going to. But we are going to want to test a handful of the different address sources. So right now we're just doing the register direct. We also want to write a test for register indexed, register indirect, and register indirect auto increment. So What this does is it's an offset of the register, so like 4 bytes from whatever register you pass in. This is dereferencing the register and then using that address. And then this is deregistering the register, taking that address, and moving the register forward by 1 or 2. And I'm not sure how you specify whether it is 1 or 2, but we'll probably need to figure that part out as well. So the first thing I'm going to do is I'm going to set up another test. Actually, we can just copy this. Call register direct. And this will be register indexed. And I gotta see what we ended up doing for this. We said it was a tuple of the register and then the offset. Okay. So the register and then the offset. We can do like 4. Operand width should be still 16. Should still be call. And we're going to have to add one more assert equal inst opcode operand width. Are we not pulling out the next value? We're not. Okay. So that's another thing we have to add in is we're not currently passing in the operand. An operand, this can be an I-16. We might need to bring this up. Maybe not. I don't know. I think we'll be okay for this for right now, but we may need to fix that. And this would end up being did we not implement the rest of this? We didn't. No, we did. We don't need. I think we'll end up adding this in and changing this as well. I don't really love this. But we do have access to it. Yeah, so we're good here. We do need to get the correct data. And to do that, let me get a terminal open with Vim that we can actually like go and use as a scratch pad. So we need, how do I make this? No, that's not really what I want either. That's what I want. There we go. Perfect. All right. So for the call, we're gonna do 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, and then our AS, which is 2 bytes or 2 bits, and it's gonna be 0, 1, and then our register, which is 9, which would be 1, 0, 0, 1. So this ends up being 1, 2, that's 9, 9. So if we do this, I think this should all be correct. Variant or associated item not found in addressing mode. Register indirect. Oh, indexed. Do we not do this? Oh, just indexed. What do they call it here? Oh, just indexed, okay. All right. And then we got to make this a real tuple. So the test failed. Oh, because we forgot the 0, 4, 0, 0. Except it's the wrong test. Oh, fuck you, come on. Yeah, so we gotta add it to the right test. Cool, and that passed. So we are currently properly decoding this. This gives us 4 bytes. We can test this with -4 as well. So 4, 4 is just that. So if we do 4, it'd be 1, 0, 1, 1. What is that? That's it's 8, 9A, B. That should be -4. Interesting. So what did we get? Huh. Are we not doing our conversion? So that would be... Yeah, we're not. So caught it. Let's complement. I think this is a uint, which is the problem. Expected a uint and found an. No, we are. Is our code wrong for this? For the ones complement code? So we're checking the high bit. I think this code is wrong. I think we're XORing against only the nibble what we need to be doing it against the full 16-bit value. No, it's yeah, that's 16 bits. Why is it not? Did I update the wrong test? Oh. That's the problem, is that we're actually doing one's complement, and we don't want to be doing one's complement. We want to be parsing it as a one's complement number. My original code, I think, was what I wanted to be doing before we did this change. This. Where we and flip it and yeah. So we're gonna do val that fixes it. Okay. So there we go. That gets us the correct negative value there. We might want to from U16 complement. So that might make sense to do. It looks like our test is succeeding though. Let's implement register indirect. So we can pass in so this should be an absolute value here. This is indirect. Take me to the. Did we do index? Yeah. Indirect. Take me to the declaration. Control B. And then this also needs to be a U8 with a U. This one I'm not sure is how you get the 1 or the 2. I think auto increment we just need to register. We don't need it because it's in the register. Right. So this does not need to be 16. Like it's basically the same as register direct, only we care what's in the register, but because this isn't live, we don't actually care. Indirect. Oh. Fuck. Indexed, indirect. So this ends up being indirect. Our AS is right before here, so it's these. Do 1 0. So this ends up being a. What happened? Did I? What did I screw up? That's good. Block is empty. Oh. We messed something up here. That. It needs to be a tuple. That passed. Let's make sure this passes. All right. We did our indirect. And then and this is indirect auto increment. So that ends up being, so that's just B9 instead. Cool. Let's go ahead and just run all these tests. Make sure nothing broke. Prefix it with an underscore. Am I not testing any of this stuff here? I guess I'm not. Code. So 0 0. I guess it'd be none. it failed. Oh no, it should be 0 because it's 16. Yeah. We don't care about all these missing. So I guess the question now is, do we want to add more like bad tests, like tests we know that should fail, like bad parse values, and maybe we don't have to right now. Like it should decode good stuff, and it shouldn't fail to decode bad stuff. It'll just return a none. So I'm not super concerned about making sure that, like as long as it doesn't choke on the bad stuff, and it can recover, that's what I actually care about. I guess we just don't want it to like improperly like give bad results for bad data. Do a couple things. First of all, open Vim back up. The other thing I'm going to do is I'm going to get into here because we're going to use Git, and we don't have the private key on the Windows machine. So we end up having to do this here. Yeah. Okay. Finish implementing tests. All right. So we can go into push. Push is where we start to actually get different sized operands. So this is where it starts to be either pushing a byte or a word, or doing something with a byte or a word. So if you were going to write some assembly for MSP430, you could write like push 16, or you could do push B 16. Now in this case, the instruction is going to be encoded slightly differently, but the operand is going to be encoded the same way. That all the operands are going to be encoded as a full word, because everything's aligned to 16-bit, as far as I'm aware. The difference, though, is that when you do the actual operation, the push itself would only push a byte onto the stack, so it would increase the stack by 8 bits rather than 16, I believe. Not 100% sure because I don't have an emulator here to do that, but I think that's effectively like what would happen and like what the difference is here. The other thing is like the encoding here is going to be slightly different, probably by 1 bit. Just that this BW field, this bit will be a 1 rather than a 0. 1 signifying that it's 8-bit rather than 16-bit. So we've got to do push. Again, this code right here is pretty gross, and I'm pretty sure we're going to end up rewriting at least a bunch of this stuff. I don't really like how we implemented it, but it'll work for now. Opcode is push opcode addressing mode is addressing mode, and operand width is operand width. In fact, we could probably just fill like all of these in right now, like pretty much like the same code. I'm not a big fan of this, but you know what? It's good enough for now. This is a swap byte. So because these are all 16-bit values or 2 bytes wide, this will swap the bytes that you're referencing. This is right something carry, I think. What's RC? Right rotate. Rotate right arithmetic. So I think this carries and this doesn't carry. It's interesting they don't have a rotate left. I wonder why. The variable opcode. Yeah, so the variable opcode does have the opcode number. The problem is that by default, Rust enums don't work the same way that C enums do, where they are just an integer. We can do something like this might work, but I'm not 100% sure. Repr C, and this makes the in-memory representation of the enum something that's C compatible. So it works with the C ABI. So you could use it for like in a C library, C compatible library. And this might be able to allow us to do that. I'm gonna end up rewriting this whole thing, I think, which is not the parsing code probably, but the internal representation, and probably some of how we build these values. So I'm not super concerned about repeating the code right now. I totally agree though that it's very bad code, and I think that I want to get a little bit deeper into it before I figure out exactly like what the new structure is going to look like, and kind of get to that point. I also want to have the tests written and be fairly confident that the tests are correct. So when I go to start refactoring it, I can verify that like I'm not breaking stuff. Yeah, it's a totally like valid question and like a very reasonable like assumption. There's like some crates which are like Rust's way of like packaging up code that that make enums like function more like the C ones. And I've done some stuff here, like I said, like the Repr C, like I think may work, but I don't want to risk breaking this stuff right now until I get the tests in place. Just because I know that this code works, as far as I can tell. The decoding and parsing, sorry about that noise. The decoding and the parsing works, and I don't want to like change the implementation until I can verify that like that's true. But then we'll probably spend some time like redoing this and making it better. I said earlier, like I already know that like displaying the data based on the internal representation right now is going to be really bad. And I think what I'll end up doing is either making an enum that has a whole bunch of different, like we'll make a struct per instruction maybe, and an enum that is like each instruction has like the data that goes with it, or we'll make like a source, a destination structure, and an instruction structure, and the instruction structure will have a source and a destination and an opcode in it. and then each of those structures will. So in Rust you have a trait, which is kind of like an interface, but basically like you have the display trait, which is used to print out the struct. So if you were to call like effectively like the toString, if you were like using like Java or I don't know what it's called in C++. I think it's like string or something like that. Or in Go, it's I think it's toString or string. It's effectively like implementing that. So you implement display, and that tells it how to print. So if if we implemented like a struct for each instruction, we could, or each type of instruction, a single operand, a conditional, or a two operand. The display implementation for the trait, the display trait implementation for each type would know how to combine the two different operands plus the instruction, and it could like properly format it all. But so that I'm not exactly sure yet. I kind of have to think about it a little bit more how I want to approach it. And anyone who wants to suggest stuff, I'm totally open to ideas. But I'm hoping by the time we get to there, I'll have a ton of tests and we'll have refactored some of this stuff around a bit so that it's a little bit easier to work on. I think after I finish doing all of these single operand ones and getting tests written, we'll probably break all this out into separate files, just so I can stop scrolling through like what I'm sure is going to be somewhere around 1,000 lines by the time we're done implementing all of these. The only difference here is we're building stuff. Yeah. Finished building single operand instructions. So let's get the test written. Which, realistically probably not the most exciting part, but is very important, especially for this type of stuff where like precision matters. So RRC would be 0001, 0000, 0. That's 7. 7. So we're gonna do first as 0. Our AS. Oh, this is gonna be a lot because we're gonna have 4 times 2. So we're gonna have 8 different variations of this. Maybe more than 8 different variations of this. And 0, 0, and I guess we'll use 9 again for the register. So that would be 1, 0, 0, 1. So we get 1, 0, 0, 9. That's RRC. That's W. And then 0, 0 is register direct. Zero, 9, 10. So this ends up being RRC. Operand width would be word, so it still is 0. And yeah. So that works. Let's shift the, not the addressing mode, but let's shift the, this to byte. So that would be there. And that turns this into 4. Operand width becomes a 1. And nothing else changes. Oh. That's correct. That's also correct. All right. And we're going to have to end up doing 2 of these because they have negative or positive values. So we're no longer doing direct, but we're doing indexed, positive. Index positive and index negative. Positive is that, and then it's just FBFF. FBFF. So this is just positive 4, this is negative 4 in one's complement. We need to change this to be indexed. And we're making this a tuple, register 9 with value 4. And then this ends up being indexed with a tuple, and it's 9 and negative 4. This same exact data here. Oh. I screwed up. 4, 0, 4, it's FB, FF. Four. All right. Let's make sure that Did I not update the... I didn't update the... No, I should have. I didn't. This should be 4.9. Let's see. Indexed. Which assertion is this? It's the operand width. This should be 1. Wait a minute. So... zero... Do I do C++? I do a little bit of C++. I'm very bad at it, but trying to get better at it. I'm pretty good with C. I've done a lot of writing in C, and I've been learning Rust and using Rust for the past maybe 4 years, 5 years. I have... actually just picked up this book over the holidays, which is neither a crash course or fast-paced, as the title suggests, coming in at like 700 pages. But it's C++ 17, which I looked at older content from I don't know, like C++, like 98. And I've been trying to find like a good resource to learn like the newer APIs and changes have been introduced. I know that 20 is coming out pretty soon. I think it's been ratified and like you can already get compilers that support it. But yeah, not very good at it. And the problem here is that I didn't update the opcode. This should be... I need to change the bit 6. So 0, 1, 2, 3, 4, 5, 6. This should be a 1, which makes this 1, 0, 4, oh. Did I screw something up? So... am I doing the wrong number of shifts for my operand width? where's the operand width? So we're masking off, what is this? That's 0, 1, 2, 3, 4, 5, 6. And this should be 6, that's why. That would help. Yeah, like this is exactly why I want to have all these tests written before I dive into refactoring, just because I know there's problems like this throughout the code that are going to be a disaster. All right, so that passes. Now, the thing we need to change here is the addressing mode. So this is the addressing mode means that for our byte-based addressing, it's going to be these. No. Yeah, here. So this should be. So byte-based is going to be 5 rather than 4. And then for the word-based, it's going to be 1. All right, let's go run all the tests and just make sure. All right, so everything runs, and we're gonna have so many tests when this is done. So none of the other ones are gonna have additional arguments. Like they could, but none of them will, because they're all based on the register and not based on an additional value. So I'm gonna grab these tests to base them off of, since we only need one variation of each, and all we're gonna do is end up changing the so we're going to do indirect indirect I don't know what I keep hitting that does that, but it is very annoying. All right. So the major change here is that this becomes that. So this becomes 1029 for the word-based 1029 for the word-based, and then 4, 5, 6, 6, 9 for the byte-based. That's good. That's good. And then indirect, and then this is auto increment. So the byte one is going to be, this is 4, 6, 7. Right, and then this becomes 3. Let's run all the tests. All right. Tests. For was it RRC? Fix. So I think at this point, like all of this is now correct in terms of our parsing of it. I think that probably was the last part we hadn't tested yet. Still possible that this is maybe wrong, but I think that this is correct at this point. So we can do swap bytes. And now the cool thing about this is all of these, we can basically just copy this whole block of all the RRC stuff. And actually, so swap bytes can't take a, we don't do the, we actually want call to base this off of, because call doesn't do the byte or, that doesn't do the width. Like we can't control whether it's a byte or a word. So in this case, call is probably a better choice to base these off of. All right, so this will be swap bytes. Let's see here. So 0, 0, 0, 1, 0, 0, 0, 0. Zero, 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 1, 0. Yeah, so only 2 bits we need to change are these two in here. So this ends up being 1, 0, 8, 9. This is call register index positive. Oh, yeah, it's complaining that we've already defined these. Okay, so that's correct. This is going to be that, which means that this goes up to 9. $99.10, which means this also just gets to that. This will also just be that. And this becomes let's run all the tests again. All right. So for RRA, we can copy the RRC tests and verify through that. I'm hoping that like once we start redoing the refactoring and get the code rewritten, we can also refactor some of the tests and make like maybe do it from a table or something, so we don't have to have so many functions. Like there are so many. Like we're gonna have probably 100 tests in here. Probably around 100 just for the decoding and parsing. This probably needs to get tested. I guess we could write like a pretty quick test for that, but not important right now. So this is the RRC stuff. All right. We're gonna do this the lazy way. RRC with RRA global. Let's make sure that we didn't do anything bad. It did. Does it not know how to do this? Yeah. Make sure that, yeah, there we go. Putting the %sign was the problem. RRC opcode RA opcode. All right, cool. So to do this, RRA is going to be 0001, 0000, 0001, 0001. Oops. 0001, 0001. And that's always the same. And then this one is always going to be 0. And this is our BW. And this is our, so it's only these 3 bits basically. You change 1, 1, 1, 1, 9. Interesting. So what did it? Range and index 4. Panicked at range index 4 for slice length 2. This is just the register. AS. Oh. It should be 09. So that's 09. And then this would be 49. That's correct. That's pretty cool that all it is this one bit. Let's go back to the top. Oh my god, this takes forever. Control Shift F10. All right. So that's test for RRA. So we gotta do sign extend, and then we gotta do push. Let's get some water real quick. I think the tests are going to really explode when we get down to here, because we're going to have a destination and a source, and like both of them are going to be able to be negative or positive probably, and there's additional addressing modes. We also haven't done any tests against PC, and we haven't done any tests against SR or CG. And we realistically probably need to do all of these addressing modes and these addressing modes for all of these instructions. Which kind of sucks. It's going to be a lot more. So sign extend will be the same as swap bytes. We can just go steal that code and do the same thing we did there. Swap E, SXT. B. All right. So SXT is 0001 0001 1 0. So this ends up being 1 1 8 9. Oh yeah, this has become 3 because it changed the addressing mode. So 3. No instruction returned. That's 8-9. One. No, it's 9-9. Indianness. So that becomes that. That's A9. And then push is the last one that we have to implement. Once we've done push, once we've done push, I don't know that I want to bother doing the other addressing modes right now for the other registers. It just doesn't sound super exciting because it's basically just copying and pasting a bunch more. But maybe it makes sense to do that. Just so that we can get to the point where like right now we're not doing any of this parsing. So I don't know if it makes sense to do any of the it probably makes sense to do the refactoring for like all of our internal representation before we dive into this. But after we write the tests for the other addressing modes, just because it'll be less tests to refactor, but we're probably not going to screw any of like this up. This won't be written yet. Push is like the same as RRA. Call RA push All right, so let's see what a push instruction looks like. Push is 0001, 0010. Zero 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 one zero zero 100, followed by our, this is our width, this is our addressing mode, nine. So this, so it's 1 2 0 9. Indexed positive W. Yeah, so this indexed is 1. Indexed, yeah, 0 1. So this is 1 2 1 9. And so it ends up being that. So that's 4 5. 1 2. All right. Control Shift with F10. But I want all of them. How do I run all the tests? That was Control Shift. Control Shift F10. All right. So those all pass. this is crazy. I mean, like we're over 1,000 lines of code, and the majority of it is just tests. But you know, we're gonna know for sure that our disassembler is correct, at least. So yeah, this is where all of our 2 operand instructions are going to go. Where's the refactor? Yeah, rename. That's the one. So this is the one thing that's kind of shitty about using the Vim plugin for CLion, is when you want to start refactoring, it doesn't work as well. Single brand register mask. Was it shift? And I used to know all of these. Shift F6. Single operand opcode mask. And then single operand width mask. Yeah, I think we'll end up cleaning up a bunch of this stuff as well. Some of these constants, renaming them, moving around. But like once we have all these things defined, it'll make it much easier to do the refactoring. Okay. Mask const. The operand is in memory. Oh, so I wonder, it's like, we know what the what is it? MSP430 SR register. We know the register set here. Like these are all the values. And it's interesting that like that these are the constants that you get is a 4 and an 8 for SR. Because 4 and 8, I mean, all you would get for that would be CPU off and V. So V is, what is V? C is carry, Z is 0. What is V? Clear V to 0. Anyway, I think I'm gonna call it for the night. We got most of the stuff done that I wanted to. I don't really feel like sitting here and implementing the missing tests for these right now. I also want to read up on SR and figure out exactly what those addressing modes mean, because I don't quite understand what the use case is yet for those specific ones. And I don't know what CG is yet, but I'm going to figure that out. But we're looking at almost 2 hours in at this point. I think this is a good time to stop. So, yeah. The code's up on GitHub if you're interested in checking it out. Available here. Probably keep going in this branch until we get the missing tests in, and then we'll merge this into master once that happens, and then from there I think we'll do the refactor, clean everything up, get things broken out. We'll get missing tests for this written, and we will redesign our internal representation of the data, as well as update the tests to work around that. And then once we do that, we can go and we can start implementing the 2 operand arithmetic instructions. So I mentioned a little bit earlier about how I wanted to do the printing of instructions, and I think that's how I'm going to end up implementing emulated instructions, because the internal representation, we don't really care about the whether or not it's an emulated instruction in the internal representation, because you're probably not going to base anything you're doing on this. And I might be totally wrong about this, and we can figure that out when we get there. But for the actual goal of using Binary Ninja, the behavior is already defined by the opcode because they're emulated instructions. So I think what I'll end up doing is implementing display. When I implement display, based on the instruction, it will figure out whether or not it's emulated or not. And this may or may not work. I'm not sure if we'll have access to enough of the data at the time to make that determination. But I think we can figure that out once we do the refactoring, and decide if that makes the most sense. Otherwise, what we can do is we can make it so that any of the instructions that are emulated, or that support emulated instructions, so like add, move, bic, dad, sub, bis. Like they all have like a boolean flag as to whether or not, based on the current operands, it is emulated, and then what the alternative instruction is based on that. Anyway, have a good night, everyone. Hope you enjoyed the stream. Don't forget to subscribe if you want to see more of this, and I'll catch you next time. Bye.